Good morning, everyone. A very warm welcome to you all. It's a very important day for all of us. 2nd of March, Electronics, Packaging, Design and Manufacturing Conference, the inaugural ceremony of EPDMC 2026. It's a flagship program that is happening at Manav, Rachna under the guidance of IEEE EPS and mentorship of various industry leaders and corporates across the world. It's an exciting day, and not just because of the fact that we have an IEEE conference, but because of the fact that there is so much learning that is going to be there through the Power Pack sessions across the 2 days of this mega conference event. On behalf of Manav Rachna Educational Institutions, I would like to extend a heartfelt welcome to all the dignitaries, all the industry delegates, academicians, and students who have gathered here for this particular conference. And before I kickstart the proceedings of the conference inaugural function, I would like to give a brief gist of what we have done so far. So the plan started, I think, a year ago when this was ideated amongst a core team that we should do something across electronics packaging, because this sector in India is coming up in a big way, and a lot of corporates are coming up and setting up their plants in India. So as academia, what we can do to make sure that we have a talented workforce ready to take on those challenging roles in the near future, and at the same time, how we can learn from each other. So this got conceptualized that let's take on something called as EPDMC and try to bridge this gap, try to have people on the same floor from industry, from academia, let them exchange their thoughts, their ideas, and get some directions on where this industry is going and how, as academicians, we should be ready for that next wave, which is already there on the floor. So when you are in the classroom, you have very confined space, you have great dreams, big dreams. It's important to align it with where industry stands and where it is expected to go. And it can't get bigger than this, where we have stalwarts from industry. President of SEMI, Ajit Manocha sir is here, Ravi Mahajan sir is here. We have representation from Applied Materials, PTW, KLA, ICEA, and so many talented people who have actually done it for the country, for the globe. They are here today in the campus of Faridabad to share their knowledge with you, to share their vision with you, to let you know what exactly needs to be done to get ready for the next big wave. That is semiconductor manufacturing. So without further ado, I would like to request the dignitaries to please gather for lamp lighting. And we can start this process by Saraswati Vandana. Please. A huge round of applause.
Pama gama pani dada, nisa papa pani mama, napa mama gama pani sa. Ma Saraswati Sharade, Ma Saraswati Sharade, पूर्ण इस अज्ञान उदधि से, पूर्ण इस अज्ञान उदधि से वीणा पानी तार दे, तार दे, तार दे, माँ सरस्वती शारदे, माँ सरस्वती शारदे, 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 माँ सरस्वती शारदे,
much. Huge round of applause. Now, may I request Chair EPDMC 2026, Dr. Ashwini Kumar Agarwal, to please come on dais and share some inspirational words about EPDMC 2026, how it was conceptualized, and where we are heading towards. Thank you.
Thank you, Umeshji. Respected dignitaries. I have 10 of them, so I'll not call all of them by name, but really appreciate your being here. Industry and my dear students, it's a pleasure actually being here today. This is actually the culmination, as Dr. Umesh has talked of a concept that was thought about a year and a half back. And I was so strongly supported by Dr. Ravi Mahajan, Intel, and on the board of governors for IEEE, a major leader in the electronics packaging industry, a thought leader, and he encouraged that we should actually create an active EPS, Electronic Packaging Society chapter here for Delhi section. Those of you who don't know, we are 8,700 people strong in the IEEE Delhi section, and EPS was one society which was missing. So we started it, and we have actually built up a huge momentum for it at this point of time. The Delhi section teams were surprised. We did not take any resources from IEEE last year, and we still did 17 events, and we conceptualized the EPDMC a year back. It's been a journey. It's been a journey. We have reached out to the academia for their contributions on the academic tracks, to the industry for their support for making this event happen, to the global leadership like Ajit Manocha ji, who agreed that he would endorse this first event that we are doing, which actually sets a pace for building the EPS momentum in the northern region. So when we actually looked at it, there were also some mandates back from Ravi. So he wanted this to be a forum where we actually do some meaningful discussions. He wanted me to add quantum technologies, a track on it. He was very clear that we should actually look at a discussion that brings out the strengthening of the electronics ecosystem for India. And when we talk of strengthening electronics ecosystem for India, there's actually something interesting. We no longer talk about can India do manufacturing. India has established that it can do electronics manufacturing, and it can do electronics manufacturing at scale. The real challenge here is, can we actually look at building value in that electronics manufacturing? And that's where a lot of focus is going on at this point of time. So if you actually take a look at it, today, India's challenge is more about integration, about bringing supply chain in, making sure all elements of the value chain, we find our niches where we can contribute productively. So to a great extent, this conference, as we conceived it, is not like a normal conference. It's much more on how we can bring about that value integration. So when we have KLA here, Narayani has supported us for this event, I can tell you, when we actually look at it, what we are trying to do is we have an interface with SCL, and right behind you is SCL. Rahul Khadelwal from SCL, and you should actually network with him, which is a major investment which is coming place in the Delhi Northern region from the government side. But it's not just them. We also have other players. Sesra will be here shortly, and Sesra is the first OSAT in the country, and they started with a 150 crore investment, but actually, as Sanjay ji will hold the flag, they went for an IPO, they grossed about 1,000 crores of investment support in that particular IPO. It will grow. They are very clear they'll grow, and they have plans to do that. So their operations, they are the first commercial OSAT in the country, and they're really growing that operation out. If you actually take a look at it, we have people from the industry here. They should actually look at interfacing with Hariba. Hariba is showing a product called Coach in this particular forum. Creates a class 1 clean room for a test bench in less than half an hour, and it is actually very affordable. So do you really need SEL everywhere, a class 100 clean room? You can't afford that sort of an OpEx when you have solutions like this. Getting those solutions in is what is adding meaning to this particular forum. I think at this point of time, the key message I want to give is, clearly at a time when advanced packaging, chiplets, photonics, heterogeneous integration is redefining the global electronics, discussions here are going to help India move from pure assembly-centric participation. It will help them to get into architecture-led design. It will help them to move into a strategic value capture. This transition from volume to value capture is what we would like to see EPDMC contribute to the global community, to the nation. On that note, I think I'll sign off and request Ureshi to take ahead.
Thank you very much, sir, for your kind words and giving the directions. One thing is very sure that manufacturing ecosystem in India is actually growing at a very different pace altogether at the moment. I was there in the fabrication facility of Globe Capacitors, and JJ is here. So I can say very clearly, if a washing machine is getting manufactured in USA, probably the capacitor of that machine is coming from Faridabad. So the point is, yes, India has done it, India can do it, and India will do it, is what we believe in. And without further delay, I would like to now request our Honorable Chancellor, Dr. Prashant Bhalla, sir, to please come on the dais and share with us the vision behind creating Manav Rachna, and at the same time, how he looks at the global workforce development in the area of semiconductor, and how our university is progressing towards ensuring that the kids get the right blend of academia and industrial exposure so that they are ready for the next wave of manufacturing in the semiconductor domain. So may I please invite our Honorable President, Chancellor Dr. Prashant Bhalla, sir, on the dais for his address. Thank you.
Good morning, everyone. Respected Shri Ajit Manocha ji, the President of SEMI, Dr. Ravi Mahajan, Dr. Suraj Rangarajan, Dr. Hemang Bhatt, Mr. Sanjay Agarwal, Shri Rajesh Sharma, Dr. Sanjay Srivastav, Dr. Ashwani, Dr. Rohit Sharma, distinguished representatives from IEEE, particularly the Electronics Packaging Society and IEEE Delhi section, industry leaders, academic colleagues, sponsors, members of the organizing committee, and dear students. A very warm morning to all of you. It's indeed a privilege to inaugurate the first International Electronics Packaging Design and Manufacturing Conference, EPDMC 2026. At the outset, I extend my sincere gratitude to the Institute of Electrical and Electronics Engineers, IEEE, especially the EPS and the IEEE Delhi section, for their continued support to the scientific and engineering community. I think conferences of this stature thrive on credibility, collaboration, and shared purposes. I also deeply appreciate the entire organizing committee, the Manav Rachna Innovation Incubation Foundation, led by Dr. Umesh Satta, the Department of Electronics and Communication Engineering, our industry partners, sponsors, and volunteers whose collective efforts have made this conference possible. I think we have seen India's growing strength in electronics and manufacturing, and India today is witnessing a decisive transformation in its industrial and technological landscape. Electronics production in the country has crossed the $100 billion mark and continues to grow rapidly. The electronic system design and manufacturing sector is emerging as a critical pillar of India's economic growth. India is already globally recognized for its strong semiconductor design talent. Today, we are steadily strengthening the capabilities in manufacturing, packaging, testing, and electronics integration, I think creating a more balanced and resilient ecosystem. I think this shift reflects long-term national vision and sustained effort, and we must acknowledge the strong and strategic leadership of the Government of India in accelerating this momentum. Under the guidance of Honorable Prime Minister Shri Narendra Modi, semiconductors and electronics manufacturing have been identified as priority sectors for national development and technological self-reliance. The Indian Semiconductor Mission and platforms like Semicon India demonstrate the country's commitment to building a comprehensive semiconductor ecosystem. The Ministry of Electronics and Information Technology, along with other ministries and state governments, have played a significant role in enabling policy support, attracting investments, promoting domestic manufacturing, and strengthening skill development initiatives. India's semiconductor journey today is supported by policy clarity, investor confidence, and growing institutional participation. And as we speak about growth and ambition, it's important to recognize Indian companies that have been contributing consistently to this ecosystem. Organizations such as CDIL Semiconductors, Sahasara Semiconductors, and component manufacturers like Globe Capacitors and Deki Electronics represent the strength of indigenous electronics manufacturing capability. The semiconductor ecosystem extends beyond the fabrication facilities. It includes components, packaging, testing, materials, systems integration, and I think each layer is vital in building a globally competitive value chain. And it's particularly meaningful that this conference is being hosted in Faridabad, a city with a rich industrial heritage, and Faridabad has evolved over decades as a major manufacturing hub, especially in the automotive and engineering sectors. And it has been supported by micro, small, and medium enterprises and large industries, and that form the backbone of India's manufacturing ecosystem. And I think the broader Delhi NCR today represents one of India's most dynamic industrial clusters with strengths in automotive, manufacturing, electronics assembly, research and development centers, and component manufacturing. I think with the growing emphasis on electronics and semiconductor manufacturing in and around Delhi NCR, the region is witnessing a natural convergence between automotive electronics, electrical vehicle technologies, industrial automation, embedded systems, and advanced manufacturing. So this regional strength definitely positions NCR as a strong contributor to India's semiconductor and electronics growth story. And I think the success of this transformation depends on deeper collaboration with associations such as SEMI, Electronic Sector Skill Council, the Electronic Industry Association of India, the India Electronics and Semiconductor Association, the India Cellular and Electronics Association. They all play an important role in aligning industry standards, the skill frameworks, and the policy advocacy. And there is a tremendous opportunity to further strengthen the structured engagement between industry bodies and academic institutions through curriculum alignment, the joint certification, internships, apprenticeships, and knowledge exchange programs. And I think that's where universities, they can really serve as a talent hub, and they can, through their initiatives, contribute and make this sector a truly a resilient sector that our government envisions it to be. The goal is simple: to ensure that students graduate not only with academic knowledge, but with professional readiness and confidence to contribute meaningfully from day one. So we talked about the hub and the spoke model and the hub-spoke-spike model, which we are trying to envision, which emphasize on a strong hub, strong institution with advanced laboratories and expertise, connected with the spokes, connected to tier 2 and tier 3 institutions. And then it leads to meaningful partnerships, innovations, and the knowledge exchange, and ultimately employability for the students who are connected with our ecosystem. I think this approach ensures that semiconductor and electronics development reaches across regions and cities, and it strengthens the national ecosystem. I again extend my sincere appreciation to all the distinguished speakers, industry leaders, academic colleagues, sponsors, faculty members, researchers, and students present here today. Your participation reflects a shared commitment to building a stronger electronics and semiconductor ecosystem for India. With this conference in our shared vision and collective strength, I formally inaugurate the first International Electronics Packaging Design and Manufacturing Conference, EPDMC 2026, and I wish all of you a highly productive and inspiring conference. Thank you. Thanks a lot.
Thank you very much, sir, for your encouraging words and giving the vision to all of us how Manav Rachna is looking forward to strengthening the semiconductor ecosystem through its initiatives. Now we have Chair IEEE Delhi section, Dr. M.N. Huda, who is not here at the moment, but he is connected virtually. So is he there at the moment?
A quick correction.
Okay.
Dr. Huda's had a medical emergency. He sent me a WhatsApp. He's not able to join in. I'll take the note for him and then pass the baton on to Ajit ji. So A quick message from Dr. Emin Hoda, the chair of the IEEE Delhi section. Absolutely delighted to have this event unfold out today. He could not be here because of a medical emergency, though he planned to be addressing us virtually, but he's constrained at the hospital. At this point of time, the key message for everyone is the IEEE Delhi section is absolutely delighted to support the EPS chapter. They have 8,700 members. This is the 50th year, the Golden Jubilee year of IEEE Delhi. They have an ambition of taking the total membership from 8,700 to 10,000. And EPS membership is expected to grow tenfold in this year. So look forward to make that number happen. Thank you, and I would like to invite invite Ajit Manocha ji for his address to the community. Sir, your presentation is here. So you can move from here.
Good morning. Oh, come on, guys. I thought the young generation will be full of energy here. Good morning. That's better. It's really such a great honor to be here. And to all the dignitaries on the dais and in the audience, it's really an honor to be here. Every time I go to an educational institution, I actually get more inspired. I wish I was sitting as a student, because there's a lot to learn for me. And especially in this industry, in semiconductor industry, we're going through a massive inflection point. I don't think there has been an exciting time in this industry as it is now. And the reason for telling you is, if you are not really totally tuned into semiconductors, do it now, and you will never regret it. And you will have a much, much better future if you are totally believing in this. And if the journey hasn't started, make it happen today. So before I talk about the advanced packaging or heterogeneous integration, let me give you a big background about the industry, because I talked about it, that why this industry is so exciting. And I'm sure that you all hear the word AI 100 times per day, at least 100 times. I mean, that's a household name now, AI. And I know Modi ji calls it America, India, and there are many, many different acronyms for AI, and probably I'll give you another acronym today. And of course, AI is fueling the growth. So before I go further, SEMI, I'm the president CEO of SEMI. SEMI is a global industry association with 4,000 companies as members. And it was founded 5 years ago with the view, when industry was in very infancy stages, a lot of companies were designing their own semiconductor chips, equipment, materials. For example, I was in Bell Laboratories. My first career, my job in US was in Bell Labs. And Bell Labs was part of the big company called AT&T. We did everything ourselves, making silicon wafers, design, wafer fabs, assembly and test, and product design, you name it. Everything was done within Bell Labs. Similarly, IBM was the same way. But after a few years, this industry started growing, so then there was a kind of much more growth in the equipment industry and material industry. And then the visionaries thought that if we don't set standards, then there will be so many niche machines, it will be very expensive to build semiconductors. So the SEMI was formed with 3 pillars. One pillar was standards, so that we all have the multiple choices of tools, as well as the right kind of material specification, so that we are not struggling with the different choices. Plus also it will bring the cost down. And the second pillar was environmental health and safety. And that's an important pillar. During my time at semiconductor industry, when I started in 1980, we use less than 10 elements of the periodic table. And plus we use all the nasty materials, gases, toxic gases like silane, diboron, phosphine. And there was a very big concern that if we don't really pay attention to safety, we can have many, many accidents in this industry. So SEMI was chartered to get the industry body together and address the safety issues so that when companies are starting their production, they will follow those practices. And I can say with pride that to date, there has not been any major accidents in this industry. And today we use more than 90 elements of the product table. Now 90 elements sounds a small number, but each element produces, has hundreds of compounds. So we're talking about a lot of chemicals that we use in this industry. And the third was the thought leadership. So we started this platform called Semicon events. So with this Semicon West was the one in California that started in 1970. And there we bring the who is who of the industry and share the forward-looking vision. So that promotes innovation. So that was really the basic principle. But again, I just want to give you background if you haven't heard about SEMI. But today the SEMI has advanced a lot with much bigger platform and programs. So we have virtually all the research institutions of Europe, Asia, like IMEC, Fraunhofer, Leti, and IEEE is also a partner, and ITRI from Taiwan, and many others. They're all partners of SEMI. So the point of telling you this is that if you do come to Semicon event, you will probably find all the important institutions of the world under one roof. Now, just the last column on this slide, I hope you can see it. There a big focus of SEMI is, besides the Semicon events where we enable the ecosystem, we bring like thousands of companies into an event and they promote their products. And the countries which are in early stage like India, it is a big deal. So today, as we all know that geopolitical issues are tremendous. Actually, there are two words that I have been using in last 18 months. One word is exponential. The second word is unprecedented. What do I mean by that? Exponential means our industry is growing exponentially. This industry used to be known as a cyclical industry, either high growth or high decline. So feast or famine until 90s. Since this millennium, we have gone through a total transformation. There were three waves which I will talk about. One wave is IoT, which is the Internet of Things, and that is leading to connectivity of the people with machines, machines with machines, and countries with countries, cities with cities, you name it. It's connecting the whole world. And IoT has really fueled the growth. And the wave which is going this decade is AI. And the third wave, which is around the block, is the quantum. So the exponential word, and I will come back to that in a bit more. And the then unprecedented, the number of geopolitical issues are unprecedented. I have been in the industry 45 years. Until 2017, I never really worried about any geopolitical issues in this industry. But today, every day, we hear something new on the TV, and these geopolitical issues are unprecedented, and they're creating a lot of impact, not only on this industry, but on our lives as well. So SEMI has a big role to play, where we actually help the industry navigate through these issues, not only industry, but also the governments to navigate through the geopolitical issues. Why I'm saying this? Our philosophy, we are country neutral, company neutral. I don't take side of any politics or political party, but we talk about the policies which directly impact our industry, and we only support the members or the companies or the countries who comply with the international laws for IP protection and national security protection. If those companies are labeled as anti-compliance, we kick them out of our membership. That's the principle. So I'm spending a lot of my time with the governments around the world. In fact, in 2025, I've been on the international trips twice a month, 2 trips per month, and spending half the time or 60% of the time with the governments, helping them to navigate through this. Basically, my message has been, do not confront with any country. Keep your head low, focus on your strategy, execute on your strategy, and keep moving, because geopolitical issues are going to remain with us and maybe increase. Did anybody anticipate that last week we'll have a war between US and Iran and Israel and Iran? Did anybody anticipate the war between Afghanistan and Pakistan? And who knows what will happen tomorrow? And let's not even worry about it, because you should focus on things we control. What we control is what happens in this Manav Rachna, that you are trying to get the best education in semiconductors, which will transform your lives drastically. And if you don't focus on that, then the transformation will transform you differently. So the second topic is workforce development. I don't think I need to spend any minute on that. I think Umesh is very familiar with what SEMI does. The industry is growing through exponentially, but one sad thing is STEM education in the Western world, whether US or Europe, has gone, and STEM education enrollment has gone down by a factor of 3 in last 3 decades. In Asian countries, and I think you will all agree with me, in India especially, when the child is born, the first day parents start saying, "Mera bachcha to doctor banega ya engineer banega." Are you familiar with that? Yes? So in Asian countries, STEM education is still popular, but the number of children to couple has reduced by less than 2. Yes, less than 1, sorry. The average used to be 2+, now it is 1-. In Taiwan, in South Korea, in Japan, it's 0.6 or 0.7. So the overall STEM education population, STEM educated population, has gone down by less than 2, while industry is growing by more than 2, factor of 2 in last few decades. So there's a huge potential. That's what I meant. You have a future in this industry. Nobody with semiconductor background will be looking for a job because there is so much demand. Then another 2 topics on the importance, I will not spend much time because of the limitation on the time, but the next 2 big topics which SEMI is focused on, cybersecurity and AI revolution. And again, some of this will come clear in my presentation today. When I talk about the industry growth, this shows the slide that our industry was roughly $500 billion in IC revenue. IC stands for integrated circuit revenue. And there was a unanimous agreement until last year, by 2030, our revenue will be $1 trillion. And I was one of the big promoter of that forecast, but I was so wrong. Actually, it will be $1 trillion this year in 2026. And now I'm putting a stake in the ground. There will be $2 trillion by 2035. That's really very exciting. That's what I meant. There's never been a better time in this industry as it is now. So I wish I was a student graduating from Manav Rachna and looking for a job. I'm sure I'll find, if I'm Manav Rachna student, I'll find a job before employer looks for me. So now, just a very snapshot of the way growth is adding to the GDP. It was the PC boom before 2000, then internet boom during 2000 area, smartphone booms in the first decade of this millennium, and now the AI boom. And actually, I think there should be next one is quantum boom. That's going to happen. So there's no shortage of reasons for growth. In the past, we used to say, God damn it, we need a killer application to have the growth. Right? Jaswinder, you remember those days? So Jaswinder has been in the industry probably 100 years, and another veteran of the industry. what is happening now? I talked about the three waves, IoT wave, AI wave, and now quantum wave. And actually, they are already interdependent. AI is accelerating quantum, and quantum is accelerating AI. Again, not going to go into the details, but these are the you can say, take as the buzzwords. If you're not involved with these buzzwords, I would say just get involved, and you will learn a lot from this. So here is an important slide. This slide was shown by Intel, not by Ravi, but one of his colleagues just 3 months ago in one of the events. And he talked about how AI, now first of all, AI stands for artificial intelligence, literally, right? That's not my interpretation anymore. I call AI stands for accelerating innovation. And that's another reason that I think the AI boom is so important. It will create more innovation, and that means more applications and more benefit to the humanity. And I'll talk about that in a minute. Artificial narrow intelligence has been the well-known, well-understood, which actually lacks the human intelligence, which is whatever you teach the machines, and the AI has been helping with the machine learning and all kind of language models and so on. But now we're going to the era of artificial general intelligence, which is more like a human-like intelligence. And this gentleman from Intel, he said the next phase is artificial superintelligence, where the intelligence will exceed the human thinking, human knowledge, human intelligence. And his view was that there will be another 15 years. And coming from Bell Labs, where I also try to think, not today or just tomorrow, I think about 10 years. That's the way we have been trained in Bell Labs, think future. And I said to him, I said, Dr. Naga, 15 years is too late. This is going to happen in 5 years. And he didn't argue with me, but why did I tell him? I rarely watch movies. There's not enough time. I watch a Bollywood movie. I don't know how many of you have seen this movie called Teri Baaton Mein Aisa Uljha Gaya. Have you seen that movie? If not, see it. You will appreciate it. I mean, basically, I used to watch science fiction movies in my early days of career, and science fiction has become facts. And I remember there was a movie, TV show in US, Night Riders. There was a car named Kit. And today the car I drive in US is better than Kit. And so all those become reality. In this movie, there's a role of a humanoid helping Shahid Kapoor, the actor, and Kriti Sanan is the actor. She is the actual humanoid. And the way the story goes, it really gave me the feeling that the humanoid is going to become an integral part of our lives. Why I'm saying this? I mean, we all have elderly parents or people like me becoming elderly, and I think elderly parents need a lot of help. The young students, young children don't have the patience to put up with what the difficulties that the elderly people have. I think humanoids will become the best companions for the elderly people, plus also other things they will do in the house or in the business. I think that's going to happen in 5 years. So ASI, the superintelligence, is happening in 5 years. And that's why the innovation part of AI, accelerating innovation, is going to make it happen. So watch that movie and it will give you food for thought that what it means for us in our lives. Now come to this packaging story. I'm sure you all have heard of Moore's Law. Actually, Modi ji, 3 years ago in one of the conferences, I was with him in Gujarat, he said Moore's Law in America means that semiconductor industry has to grow by factor of 2 every year, something like that, he said that. And I'm sitting at the dais listening to his speech. I said, my gosh, our Prime Minister of India, he knows what Moore's Law is. I did not expect him to know what Moore's law is. And he tried, but he said, but in India, we should follow the Moore's law. We should do din dugni, char chugni, tarakki kare, raat chugni, tarakki karenge. So I told Modi ji after that, I said, Modi ji, आपने जैसे वो कहा हिंदी में कहा है वो शायद गोरों को समझ नहीं आएगा मगर मैं उसका एक कोई ट्रांसलेट करके बताऊंगा कि मेरा कैसे कहना चाहिए. The next meeting, I rolled out Modi's law of exponential growth. And I can tell you that I never seen him smile that big. And that video went viral, that he really loved it. But saying is easy. We have to execute on that. In fact, it is happening here. I think India is very lucky to have him as a prime minister. He is a visionary guy, he understands, and I have the opportunity and honor to meet him 5-6 times in the last 3 years. And I think he's the most impressive person I met among all the world leaders that I meet. And he knows, he understands things, and he is executing on his delivery. So we announced the first semiconductor plant from Micron in Sanand, Gujarat. And we were there on Saturday for the opening of the Sanand factory. And subsequently, there have been 10 more units announced in the country. And I think that's a big thing. The next one will be Tata and Power Chip factory coming on board in maybe a year from now or 2 years from now. But this has started. So Moore's law was basically fueling the growth of the industry, and you see the top line, the straight line, and a lot of people have been saying in the industry Moore's law is dead, because we are at 2 nanometer and they're saying it's the linear progression of Moore's law is reaching the limit. There's to some extent, people are, in a literal sense, they are saying the right thing, because you cannot go below the atomic size. And atomic size will be maybe few angstrom, although now TSMC is working on 14 angstrom and maybe 10 angstrom. But without the Moore's law, there's been other activities which are augmenting the growth of the industry. So there's a lot of things have happened in between, but now we are in the heterogeneous era, the last column. We are here, that packaging is actually helping to put more functionality in the device and more devices in the system. In a layman's language, I'm trying to explain this. And at the same time, we're trying to increase the maintain the frequency limit, and number of cores per chips are increasing, number of chips per system increasing. So if you look at a package, people call it PPA, power, performance, area, and cost. I call it PPVC, power, performance, volume, and cost. Volume is 3-dimensional vertical integration. And HIR, actually, SEMI has been the big sponsor of HIR program. Ravi Mahajan, who's sitting here, he and few other colleagues from the industry launched a HIR platform in the US, and I've been the biggest sponsor and supporter of that, and very proud supporter of that, because that's really creating, definitely right now the big buzz is about what HIR can do to help propel this industry. And if you really look at this heterogeneous integration is supporting the high performance computing, the AI wave for there's a need for energy efficiency, because with AI, I think we just heard that data centers are coming in numbers in the world. There's more than $5 trillion investments in data centers. And these data centers are energy guzzlers. So AI and HIR should help in coming up with the energy efficient chips or systems which will reduce the energy consumption, and hence data centers can work. There's big focus on medical and wearables. 10 years ago, there was a big convergence between semiconductors and automotive. That's why today an electric car is not really an automotive. I call it semiconductors on wheels. And 5 years from now, you will see the human will have semiconductor inside you, and the benefit will be, instead of lifespan, it will focus on health span. means you avoid the diseases to happen so that you don't have to go for cure. You live longer and healthy. Again, this is, take my words, for the next big convergence is with medical world. And the role here in the last circle you see, HI plus AI is the solution. So I think I just want to leave enough food for thought here today for you guys. And when you are going through your coursework or your thesis work, these things will become very handy for you to elaborate on that. And here is a slide, Dr. Rajinder Singh ji, especially for you from IIT. Give a big hand to him. He is the professor at IIT Delhi. As I told you that I always try to use my Bell Labs hat still. I think the next big growth of this industry is highly dependent on the materials. As I mentioned, we got from 10 elements of periodic table to 90 elements, but there are many, many compounds, and we are in that era. So if you look at the number of applications that I'm talking about, where heterogeneous integration is going to play a big role. Now again, I'm giving you a very high-level view. I'm sure Ravi will go into much more details about all these projects. Is that true, Ravi? Yeah. So any difficult questions, you wait for Ravi to come on the board and ask him. But if you look at the advanced substrate, and then there's a list of materials, look at the compound semiconductors, all the indium phosphide, gallium arsenide, all these materials, they need a lot more research work. Optical and photonic materials, silicon photonics is really the key for the data centers. And there's a big, big demand on that. Thermal management, advanced carbon, interconnect and bonding materials. Took a number of materials, graphene, carbon. I mentioned the names just for the sake of giving you the kind of a flavor of it today. And the list is endless. And okay, you guys can have a copy of the slides, Ashwini-ji. Feel free to give the slides to the people who want it. So again, what I can say is that we are driving the global collaboration now. What role SAMI is playing here? So what we do, we bring the community together. We don't ask people to share their proprietary information on our platform. We talk about the pre-competitive information or visionary information so that it will promote innovation. And how do we do it? We have multiple platforms in the world. So Semicon West, Semicon Korea, so on, and now Semicon India as of 24. So when we talk about the exponential growth, the scale of Semicon India last year from the year before was exponential growth. It followed the Modi's law of exponential growth. And I told Modi ji that whatever happened in 2 years in India, it took 15 years in China, in US, and other countries. So again, momentum is plenty here. So I have a very high hope that India is going to go through a much faster growth given the momentum. Yes, there will be some slowdown because of geopolitical issues. And again, we should just not be bogged down with that. Focus on what you have decided to do and just keep driving the growth. So again, SAMI is also a very close partner of IEEE, and especially on advanced packaging and heterogeneous integration. And as I mentioned that without heterogeneous integration, remember the slide where I said we are here and Moore's law is taking the straight line? And that's very, very critical, that if you're not into advanced packaging or HIR chapters, please get involved. And your contribution is very, very crucial. I will say one thing. I left India 52 years ago. Of course, India didn't leave out of me. But I was in one of the events and I saw the poster session by multiple universities on advanced packaging. This was in Gandhinagar just a year ago. And when I saw the poster sessions of the graduate students, I was blown away with it. I think we have so much talent here. I think you know it. I'm just telling you what you already know. But I can tell you, you inspired me. And I'm sure you have the same thing here in Manav Rachna. And I will say that you are the future of this industry, not only for India or for yourself or your families, but for the world. So again, you got a lot to gain, lot to do, and keep up the good work. Thank you very much.
Thank you, Ajit ji. I just want to share, you talked of how, India can do bridging of the workforce development for this industry. And I'm so happy to share that today we'll be signing 2 MOUs. One will be with Electronic Sector Skill Council for their Bhiwadi project and how our children can get trained on that facility, and how we can contribute to that project. And the second is going to be with Dr. Sandeep Garg, IndiChip. He's here in the audience. He's keen to take people from Manav Rachna into his project as that project unfolds out. So clearly things are moving. I also have Morgana here as we look at adding the value to different programs. Morgana's is from 3M, and she's been one of our steady supporters on the supply chain ecosystem. And Morgana, I want to tell you, right in front of you is Sharad Mathurji from IDEMIA. And I don't think your company has mapped them that well as they should. IDEMIA is the world's largest smart card company here now in Noida. They package 66 crore smart cards a year, okay, for which they're getting 1,000 wafer starts from abroad. You need to actually look at taking that engagement up, and that's one of the value adds that's coming up from this conference, if you people can network in. And then based on the government's endorsement of the optical transceiver and the conceptualization of what can be done to X-rate the AI with high bandwidth interconnects, we do have a workshop track tomorrow, and we have industry from data centers to government to players who are active in that particular segment, along with Amber Helmi of IEEE Photonics, to give a view on the global roadmaps and how this can be interfaced with the Indian community. So it's not like a conventional conference. We're going a little deeper on what can apply for India, and I would look forward to seeing that evolve, sir. And this is entirely your vision, Raviji. So without further ado, I would like to invite Dr. Ravi Mahajan, our plenary keynote speaker. Ravi is Fellow Technology and Pathfinding, Advanced Packaging Technology Manufacturing Group at Intel Corporation. He is on the IEEE Board of Governors, and he is a mentor for us for the Electronic Packaging Society Delhi section. Ravi, your talk, your audience, please come on.
This is being set up. Let me make, last year, Ashwiniji called and he said he wanted to start a chapter. Now, IEEE chapters take a long time. He promised me and he delivered on a chapter that moved very fast. It impressed IEEE management that India has potential by putting numbers on the board. So for that, I think he deserves a big round of applause. As Dr. Manocha said, the world is moving to three-dimensional electronics. So as you look at it, you will see a lot of numbers, you will see a lot of words. I want you to leave with a few ideas in your mind. What we are trying to do is build electronic cities, okay? And when you build cities, what you do is you make sure that those cities have the right connection so that data, traffic is modulated, that power is regulated, and that it is built efficiently. And you should keep that message in mind as we go through this. Okay. My talk will be very simple. I will start by defining why we are doing all of this. Then I'll describe the environment that we are in today. I'll talk about advanced packaging as a vehicle for heterogeneous integration. This word heterogeneous integration is going to come over and over in my talk. As Ajitji also said, heterogeneous integration is the magic that will propel compute forward. I'll describe what our future should look like, and I will close with a simple argument. all of you are very, very familiar with Moore's law. I also had the good fortune of meeting Dr. Moore a long time ago. He was a very humble person. He didn't call it Moore's law. He just said it's an observation I made. But if you look at the history of human evolution over the last 60 years, this law, by definition, has been one of the most dominant forces that has driven evolution. And he made a very simple observation. He said, every 2 years, we will double the number of transistors in one unit area. Very simple logic, right? I call that homogeneous integration. If you take a wafer and you double the number of transistors on that wafers every 2 years, you will get a lot of performance. Moore's law will proceed as its own pace, and it has changed the face of electronics. But Dr. Moore was a very smart man. He realized that Moore's law is an economic law. Essentially, what he said was the cost of doubling transistors results in the reduced cost of transistors. So he said in some cases, it is in his original paper, he said it makes a lot of sense. Instead of putting all on the same platform, you build it separately and stitch it together. And this is the idea of heterogeneous integration. This is a big definition, but what you should remember is heterogeneous integration is nothing but taking components at different parts, optimizing them, making them better, and then stitching them on a platform. And the platform on which you stitch is the package, okay? This is the definition. And I will focus only on advanced packaging. Why advanced packaging? Because advanced packaging drives a lot of technological progress today. It is the apex. Think of it as the tip of the spear. It propels this industry forward. And advanced packaging will waterfall into multiple segments, multiple areas, okay? So if we look at what it takes to drive technology, we should be able to really make change if we are effective in improving advanced packaging envelopes, okay? So in summary, I have to say 4 things. If you walk away with 4 messages from this talk, I would be really happy. One is HI, heterogeneous integration, is crucial, okay? It is crucial for advances in compute and communications. It is no longer just important, but it is essential. We have to drive heterogeneous integration forward if computing has to evolve. The second is advanced packaging is everywhere today, everywhere. In a lot of areas, advanced packaging has made a major difference. And it is our role as engineers, technologists, and as part of the society to drive heterogeneous integration very intelligently. We must extend it along multiple vectors. And as Dr. Manocha said, we are very happy that he is a sponsor of the Heterogeneous Integration Roadmap, HIR, because that is where we all figure out together how should we move forward. Okay? And it opens up a lot of opportunity. I gave an interview 2 weeks ago in which I told my boss who was interviewing me, I said, I wish I was 20 years younger so I would be able to work in this field for longer. If you really think about the opportunity that is here, it is incredible. So I think we should probably all look at this and ask ourselves, how can we contribute? So what is the big picture? As all of you know, the AI wave is upon us. Everybody thinks about AI as ChatGPT or Copilot or something of that nature. Truly, AI is much, much more significant than this. This image was drawn by Dr. Naveed Shariari when he presented at IISCC last year. It shows a boat with a number of people who are approaching a tidal wave of some nature. And the real question is, how do we manage this tidal wave? And I'll show you what this tidal wave means. Heterogeneous integration is one way by which this tidal wave can be managed. If you look at this picture, what I show here is in the blue, a platform. Okay, think of this as a platform in which you take CPUs, accelerators, GPUs, you take memory, you connect that memory, you take analog devices, and you optimize them separately and stitch them together, okay? So now let me start building the analogy of the city. If this is the city you're going to build, what you have to do is look at how you design the lanes so that connectivity or data rate is improved, how you send that data efficiently across multiple elements, how do you put more and more functionality and how you make it standardized. Once you standardize connectivity, it is up to your imagination on the systems you will build. Okay. This is evidence that it is crucial that we need to take heterogeneous integration, use advanced packaging as a platform in which we build it and we drive progress in compute and communications. Okay. Today, advanced packaging is a very important vehicle for heterogeneous integration. Okay. This device that you see is an Intel-produced device where you have 4 or 5 different entities. They are controllers, they are compute units, they are memory, they are all attached. And this is not two-dimensional, there are 3-dimensional stacks here. This is the Intel Ultra processor. Okay. And you ask yourself, so why is this heterogeneous integration so important? Let me explain this using a real-life example. The Intel Ponte Vecchio microprocessor, which when it was released 4 years ago was a revolution in the industry. It is called the GPU Max series. It already has greater than 100 billion transistors. Okay. It has 47 different tiles, all pulled together. It has 5 different process nodes, Intel, TSMC, SK Hynix, Samsung, and Micron, all come together in creating this processor. And in this processor, what we do is we have compute tiles, we have memory tiles, we have I/O tiles that cause connectivity, and they are all connected by these tiny bridges that allow you to have high bandwidth, low power connections. Okay. What we are able to do is now take this one platform. You will notice the same theme come over and over again. You take diverse IP, different die that are optimized differently, pull them together on a common platform. Okay. What you also get in here is proximate memory. So if you think about memory, the role of memory is twofold. One is to act as a scratch pad for computing, so we next to the compute. If you get memory and if you connect it with a high bandwidth, very large data rates, and low power interface, you are bound to get very good performance. HI enables this. Okay? If you look at silicon processing done on a wafer, you can print a maximum of 825 millimeter square worth of silicon. Okay? That 825 millimeter square is not enough. That is one reticle. When we designed this 4 years ago, we were already at about 3 times the reticle. Our goal is to go up to roughly 8 to 10 times the reticle. Okay, so it means that we must build HI to complement homogeneous integration, Moore's law. Okay. It is essential that we develop technologies that allow you to put more and more compute, more and more memory on that die. And then there are 2 other big advantages. Every time you get a new node on Moore's law, yield takes its time to evolve. So you have to reduce the size of the die. To reduce the size of the die, you can stitch more die on the package. Okay? So yield resiliency, that's the word for it. And then time to market. Just if you want to leave a mental picture in your mind, it takes about 2 years less to design an SIP, a system on a package, versus an SoC. Okay? And the complexity is a lot less in that design. All of this says, think very carefully, and why do we not develop advanced packaging to take all kinds of things and put it on the package? Okay. So now let me start building my story. If I've convinced you that HI is important, let me tell you what importance means. Think about this again in terms of building a city. You know, cities work if your roads are of good quality. Roads are of good quality when you have multiple lanes and you're able to send a lot of traffic on those roads with high energy efficiency, as in you have fuel efficiency, for instance, right? So what is one good way of building roads? One good way of building roads is to increase the number of lanes. That's a simple logical argument. A few years ago, when I was asked to write a roadmap on this subject, actually a couple of decades ago now, what Intel did was we created a package. And in this package, we created 2 kinds of lanes. Okay, if you look at the green structures, in these green structures, we sent lines that were 9 microns wide and spaced by 12 microns, okay? And the die was connected to the package at 100 micron bump pitch. Okay? It's state of the art, absolute high quality. But what we also did, very intelligently, we pulled small strips of silicon in between. Okay? And in these strips of silicon, we created 2 micron lines. Okay? So already I have 4 times the amount of wires. Okay? And we reduced the pitch to 55 microns. Now this picture doesn't give you a good sense of what this means from physics, but I'd encourage you, take a piece of paper, if you have a piece of paper, okay? That silicon that you see here is half the thickness of the thin piece of paper you hold. Okay? Imagine now a world where we take thousands and thousands of these per wafer, millions and millions of these wafers, and cut tiny strips, handle it, stick it, attach it, and drive connectivity. This is an engineering marvel that we have made happen collectively. Okay? So now let's look at the number of wires that come from that edge. And I will not spend too much time, but let me just give you some numbers. Okay? The green wires, you get roughly 35 to 50 wires per edge of that die. 35 to 50, keep that number in your mind. As you start printing better, you go from 35 to 50 to about 100. Slowly but surely you move up this curve, you can get about 250. If I use silicon 2-micron wires, I start at 250. If I go to 1 micron, it goes to 500. If I go to half a micron, it goes to 1,000. If I go to a quarter micron, 4,000. 4,000 per millimeter per layer. You increase the number of millimeters and the number of layers, you have a huge number of wires. And this is available today. There's a wide range of capability even today. We can build a lot of these. Okay? And Intel has introduced another innovation that will come to the market very soon, which will also make a difference. It is called EMIB-T. EMIB is the silicon bridge. In EMIB-T, what we are going to do is to send voltage directly through the thickness of the silicon. We will have multiple controls, and we will have local capacitor which will improve performance. This will revolutionize the way we send memory. HBM5 will utilize this class of technology, actually HBM4. Again, there are lots of numbers here, but let me just give you a conceptual idea. When we first built the first EMIB, we were sending 2 gigatransfers per second, okay, 2 gigatransfers. Today, we are at 32 gigatransfers, 16 times more. Okay? This is because once you open the door to heterogeneous integration, you get a lot of opportunity to build things. EMIB-T is useful for HBM4. HBM4 will be the next generation of memory. It will be scaled to HBM5. We also have a standard link called UCIe. We are designing this to be capable for UCIe. And if you look at that picture carefully, you will see a corrugated structure. That is where we put capacitors. Those capacitors will be the place where we will put charge, and we will boost signals. What we will do by introducing this technology is revolutionize the connectivity between different components on that package. Okay. The other thing Intel is doing, which also is very important, is we are introducing glass. You know, glass is a very well-known entity. Today, a wafer is 300 millimeter square of silicon. 300 millimeter diameter circle of silicon. The glass is going to go to 510 by 510. Intel now has demonstrated performance where we can build using glass. And this is an example of Intel having built glass. This is one of the first glass designs announced to the world. It was announced at NEPCON a month ago. In this design, we took glass as a core, we put multiple layers of routing, and we were able to embed bridges. The reason why I bring all this up is because these class of technologies will continue to propel heterogeneous integration forward. Okay. We were able to show 2 times the reticle already. The packages are 78 by 78, but you can imagine a world where the package eventually will become 500 millimeters by 500 millimeters. So this is horizontal. Now let's look at vertical, because in most structures, the vertical interconnectivity is just as important. This is a vertical interconnect that Intel built many years ago now. We call it Foveros. Just look at the picture and go from the top to bottom. You will see the number of connections become coarse. You will also notice that the white areas that you see here, these white areas are solder. As you shrink the pitch of these interconnects, the amount of solder is going to go down. but we can build these structures, and this is a very good example of engineering design where we are able to build fine pitch interconnects. We started out at 50 microns, went to 36. Today we know we can do 25, and we have shown we can get this down to 15. But as you shrink that pitch, the total amount of solder is going to reduce. Within time, we will run out of solder, but not to worry. There is a new class of technologies called hybrid copper-copper interconnects. Hybrid copper-copper interconnects is the future. This will give you connectivity way beyond what we have today. AMD already has a product out with this, and a lot of people are working on driving this forward. And 2 days ago, I was at IIT Gandhinagar, and I was very happy to see that they were also thinking of putting capability in this. So, lots of parallel thought happening in this area. Okay? So the case I have made for you is that I can take lateral interconnects and vertical interconnects. I can build efficient lanes by which information data is transferred. And companies like Intel, which are also a foundry and offer assembly and packaging foundry services, now can offer a very broad portfolio of technology. We can offer you lateral interconnects, dense lateral interconnects, vertical interconnects, lateral plus vertical pulled together, multiple stacks, and then scale the pitch. Okay. Not only can we offer this, but what we are doing is we are continuing to push the reticle amount. So if you look at the bottom of this graph, we will continue to increase the total amount of reticle area. Our goal is to go much past 5 and give more and more compute capability. So think of ourselves as architects who build a city. We are offering all kinds of features in our architecture, and we are offering all of this at cost. Okay. So why do all of this? Why spend so much money, time, and energy? Why do so many governments, research institutes in the world do this? The answer lies here. This is a graph that was published by epoch.ai. It's a wonderful site if anybody wants to really study artificial intelligence. Look at what happened since a paper was published by Google somewhere in the 2018 timeframe. That graph shows that compute demand, the total number of compute, has grown 4.3 times per year. It's a huge growth. Okay. This will not resonate very easily because these kind of graphs don't come. But today, if you were to tell a computer to learn how to speak, that computer can speak in almost no time, in taking a bunch of observations and then distilling them down to low entropy, high probability compute elements. This graph is going to move faster, which means all of us have to build HI systems which can support this class of compute growth and faster. And we will have to improve the bandwidth, like the total amount of information that flows through these systems will have to increase. We will have to make sure that these are very high energy efficient links. We will have to deliver power. Just to give you a number, a GPU today dissipates 1 kilowatt of power, okay? And they are talking about 1.5 kilowatts, eventually 2 kilowatts. The system you build it will be 5 kilowatts by the end of this decade. 5 kilowatts, just let that resonate. The amount of power is incredible. We have to be able to deliver that power. We have to be able to cool that power. Okay? And all the while we are stitching all these, we have to make them manufacturable. In other words, you have to be able to build them right. And this is what building right means. This is why interconnects matter. Again, lots of information here, but let me just quickly tell you what we are trying to do. You take a 100 micron pitch, you get about 100 connections per millimeter square, okay? You reduce that pitch to 36, that 100 becomes 772. The power goes from 0.5 to 0.25, which means we have improved it by 2 times. If you shrink that pitch to 25, you get 1600 connections. So you went from 100 to 1600. If you shrink that pitch to 1 micron or less, you get 1,000,000 connections. And the power to send information across this is 0.01 picojoule. Energy to send information is 0.01 picojoule per bit. This is a very exciting time to work in packaging because you can get so much performance if you are able to build the systems on the top right. And this is part of the heterogeneous integration roadmap. Okay. I won't spend too much time, but let me show you 1 or 2 graphs here. We now, and part of the heterogeneous integration roadmap is I built this plot. we can increase bandwidth, the total amount of information that goes across horizontally, by roughly 3.5 times where we are today. And in the vertical scale, which is much more exciting in my mind, we can get at least 32 times better. 32 times, that's the envelope. And I know most engineers are pretty good, which means when I say 32, most of them will be able to tweak the power and make this much higher than that. Okay? And then the other big area is photonics. Okay? I have been personally working on photonics for the last 10 years actually. If you can imagine sending information using electrons and complemented by sending information using photons, okay, complement, not replace one versus the other, you can, and these are actual demonstrations on the top right, is an almost USB-like connection where you are sending information using photons. We have demonstrated proof of connectivity using photonics. And you ask, why should we do photonics? The simple answer is you take an XPU of some kind, you send information to an electric IC, convert it into light, and you send it from the top. In the meanwhile, information goes through the bottom. You can send information for more than 100 meters. You can have 35% reduction in power efficiency, and you can increase the total amount of bandwidth. I said bandwidth is important. This is a way by which you bypass the bandwidth problem. Photonics is almost definitely the wave of the future. And we do co-packaged photonics so that we can improve the total bandwidth and complement copper. Okay? There are problems, but these problems are for engineers and economists to solve, so not that big an issue. I'll just quickly walk you through power delivery. As I said, these devices dissipate a lot of power. What we have to do is to take every ounce of power that comes from the wall and goes to the device and use it for useful computation, okay? You also have to be able to cool these things. You know, there are local spots that run hot. You have to be able to cool those. It brings up a lot of challenge for engineers to manage these levels of power, delivering them and cooling them. So we have to improve efficiency of power delivery and cooling. There are many solutions already in place to improve the efficiency, but it requires a lot of engineering effort. The same thing with cooling. When you cool, what you do is you take heat out in the right paths, reduce the resistance to heating. In other words, you duct heat through efficient thermal paths, and then you build better systems with better cold plates and potentially even immersion cooling to improve the cooling of the entire system. Okay. This is Intel having built parts. These are the stacks I showed you before. We use solder type materials to improve cooling, and we have demonstrated that you can actually cool these. These are the devices of the future with optical interconnects, multiple stacks, cooling on the top side. Okay. One very quick slide to show you that the part we are building is extremely complex. It has all kinds of polymers, metals integrated in it, some embedded, some sitting on top, which means these designs become very, very complicated, and to design them, you need to be able to model them, understand the physics, and to design them right. There are lots of scientific challenges hidden for all of us to solve, and the opportunity to do this is very high. Okay. The package is a complex composite, which means you have to build it right, you have to have the right materials, you should have the right process and the right design. And as Dr. Manocha said, materials will be an answer in this area. Hopefully I have, in the short time I have tried to convince you that heterogeneous integration is important. Hopefully I have tried to convince you, or I have convinced you, that this is the wave of the future. And if that is so, then we must use our time to develop a roadmap where we can collaboratively work together, because there's a lot of opportunity for research. IEEE, SEMI, and ASME together write a roadmap called the Heterogeneous Integration Roadmap. Okay? We collaborate with SRC, which writes the decadal plan. We collaborate with other institutes who write their own roadmaps. Together we talk about the seismic shifts that are happening in this industry. AI affects power delivery, AI affects cooling. It affects it in a major way. Data centers consume a huge amount of power. Improving efficiency of these systems is an economic and an environmental challenge. And that is a challenge for all of us in the next generation. Okay? There are very strong efforts to build these roadmaps, and I'll close towards at the end of my talk by describing to you the HIR, the Heterogeneous Integration Roadmap. The Heterogeneous Integration Roadmap is a group of well-meaning people who come together and try to take all these complex trajectories and pull them together, okay? It is inclusive, it is free, you can go to the webs and check it out, and it is open access, and it gets everybody in to talk about the future. Let me explain what this is. It's a systems roadmap, okay? A systems roadmap means there are all kinds of computing systems in the world. There is high-performance computing, data centers. Everybody knows this for AI. It's popular. But we also work on mobile devices. We work on aerospace and defense devices. Medical and health devices use electronics in a very different environment. We focus on that as well. Automotive electronics, we focus on Internet of Things. A variety of areas, a variety of systems require electronics. They all require a roadmap. To build these roadmaps, we need something underlying it. We must be able to manufacture properly. We must be able to integrate photonics, as I said. We must be able to integrate different kinds of sensors. We have to look at compute in a digital sense, in an analog sense, and mixed signal devices using 5G. And we have to power them right. We have to focus on areas that make this happen, like materials, modeling, simulation, design, test, thermal management. It's a very broad spectrum of areas. And this is an inclusionary, it's a volunteer-driven effort, so I ask anybody who's interested to please participate. It is our roadmap. Collectively, we will drive this forward. Okay. We are also streamlining this roadmap. Just to give you an idea, the US government had planned to put in somewhere like $12 billion in R&D. This roadmap was used as a basis of that. EU put in somewhere in that range. Even India put $500 million towards R&D. This roadmap was used to drive this. So it is a highly influential roadmap. We have symposia where we invite experts to come and talk. I just came back from a symposia which we did in California last week or 2 weeks ago. Highly successful. Lots of people came in and talked. Federal agencies routinely quote our roadmap. And we are streamlining it and publishing it every year. We call out research, so it tells you where R&D has to happen. And we even got a publication in Nature. In about 3 weeks, I anticipate seeing a paper in Nature Electronics, which points out that this area is of interest across the board. Okay. Let me end my talk by saying this. HI and the AI wave is upon us. There is no single solution, but heterogeneous integration is the way forward, and collectively we row to figure out a way to solve this. Since you're starting your career, some of you are experienced in this area, I would encourage you to take a hard look at this. There are tremendous opportunities, tremendous science, tremendous research, and lots of room for ideas. With that, I'd like to thank you for the opportunity to speak to you, and thank you for inviting me. And if there are room for questions, I'm willing to take them. Thank you.
Are there any questions for Ravi? So as heterogeneous integration takes off, the vision is going to be powered by all these incremental steps, which can be enabling the copper-to-copper connects, which can be actually getting a better I/O through photonics interfaces. We have a workshop tomorrow which will focus on that. So I'll take a discussion with you separately and connect on that, sir.
Thank you.
Okay, so without further ado, I would like to invite our next speaker on the dais, Himang. Himang Bhatt is a global product manager at KLA. KLA Tencor is a leading Semiconductor Equipment Corporation. Hemang leads the global engineering, global advanced packaging engagements, and the next generation product development. He has worked as a specialist in advanced packaging applications across Taiwan, Korea, Singapore, and the United States. As an inventor on 3 advanced packaging patents, Hemang holds an MTech in chemical engineering from IIT Kharagpur. So, which hostel were you in? You do not remember, okay. LBS? Triple M, okay, there you are. So, I was a summer scholar there. So, your audience and your presentation, sir. Let me turn this off.
Sure. Hope it stays. It's okay, I think. I can manage. Good morning, everyone. One major event unfolded this weekend was inauguration of Micron, and one is going to unfolding this week at Faridabad and Manav, Rachna. It's privilege to be here at EPDMC. I'm Hemang Bhatt, Global Product Manager at KLA. Over the next 20 minutes, I would like to connect 3 threads: complexity in semiconductor, the rise of advanced packaging, and why process control is important. By end of this talk, I would like to have a model of what is changing, why it is changing, and what is coming next. Without a further ado, let's go through the agenda. First, we'll talk about KLA's role in electronics ecosystem, where do we sit. Then I will talk about semiconductor process control. Thanks to Raviji, I think most of the basic terms are familiar to the audience, so I will not have to spend much time on there. And then I will connect AI's demand curve to advanced packaging. And then I will talk about the key technologies of which are enabling advanced packaging. We'll discuss about hybrid bonding, glass core substrates, panels, co-packaged optics. And since KLA sponsored my trip, I would also talk about KLA's solution, which are in metrology and inspection. And then we'll conclude with a key message. Quick glance at KLA. We were founded in 1976, nearly 5 decades of manufacturing DNA. We are also celebrating our 50th of anniversary as IEEE Delhi chapter. We operate across 18 regions, close to 15,000 employees. But the number which matters here is the R&D that we spent year on year. It's close to 11% of our overall revenue. And that R&D is required because of the packaging. The dimensions are changing, 3D interconnect, new materials are getting introduced every other month. So where does it fit in a broader ecosystem? So KLA works across the industry. We work with our logic, memory, and specialty partners. We have solutions in wafer level packaging. Then in order to manufacture chips and the requirements which are driven from the end markets like mobile or the AI, you need to work across the industry, but the goal of KLA is to have an end-to-end solution where you can detect the variation and defect early in the process so that you can save on your yield. So that's the goal. Now let's understand why semiconductor process control is important. Why the intensity of process control is getting higher and higher. So I will keep it simple. Since the complexity is rising, variability is rising, so you need to detect early in order to save the yield. And that's why we have a process control. But before that, what has fundamentally changed in our ecosystem? So today's semiconductor devices are no longer planar. You have gate all around the complex device, multiple film stacks, more process steps, and higher variability. Then you have a 3D NAND with high aspect ratio and more like a skyscraper. And with EUV lithography, smaller and smaller and complex patterns are getting printed on a die. So you need a solution. You need a solution. The manufacturing windows are getting narrower and errors are expensive at this point. So, and this complexity is not one at a time. It increases over and over for different process steps. So for audience, if I have to give one cool video of how it takes or what it takes to create one chip, there are more than 1,000 process steps required to create a chip, and it takes from 3 to 6 months from bare wafer to your final electric test. And that's why since the fab runs 24/7, volumes are enormous, so you need to detect the variations and the defects which affects your chip performance. And KLA's process control solution, it enables it. And when I say defect, the one which is highlighted here, we have maybe a residue in deep trench of via. If I talk about the metrology, then you want to measure a dimension, a particular dimension, but it's not within the spec. So then that's a variation for this industry. There are two key foundation pillars. One is inspection and one is metrology in semiconductor process control. Inspection is you can't fix what you can't find, and metrology is you can't control what you can't measure. So the industry has moved from basic statistics-based solution to AI-assisted classification as well as physics-based deep learning. But the important point here is signal is weak, noise is strong, and you must separate them at a scale. So the one which are marked with blue circle, those are the defects. So the defects which can create shorts, the defects which can cause issues with your process down the line and can eventually result in a chip failure. So that's what we are looking for. But AI is changing requirements, as I think Ajit ji mentioned, that AI is the accelerating innovation. So I will connect AI's demand curve to advanced packaging now, and let's look at how it is accelerating the demand across the industry. Historically, the growth was driven by PC, internet, and mobile. But today, it's more about AI. You have 5G requirements, you have data center requirements, mobile, new models are coming in. And this 1 trillion, I think we already discussed, it was supposed to be in 2030, but we will complete the 1 trillion industry by end of this year, and we will have 2 trillion, as Ajit ji mentioned, by 2035. So we are already at 1 trillion in this year. But AI is not just another end market, it's a multiplier across the markets. And since we have a diversification, the number of device types are higher, and then we have a packaging architecture, so you need to do a R&D for advanced packaging. And the performance growth here is not just the pure transistor scaling anymore. We are pushing our monolithic logic from FinFET to EUV to gate-all-around backside power, where the number of transistors are more than 100 billion. We are pushing the DRAM R&D as well, where the data rate is from 1 terabyte per second to maybe 10 terabyte per second when we are talking about high bandwidth memory 4. But the key interlock here is how do you integrate the system with help of advanced packaging? How do you ensure that with having larger size, the form factors, and how do you ensure that the 3D connect will be in a right place? And that's why AI is driving this R&D across the industry. So if we talk about GPU, so this image here is from famous NVIDIA GPU. So in GPU, we are pushing our foundries to work on design rules less than 3 nanometer and in angstrom at this point. Memory also, high bandwidth memory, we are pushing our memory players to deal with more memory versus regular DRAM. Advanced packaging is also getting large, complex, and it's expensive. So the conclusion or the bottom line is that AI requires advanced process control solutions, and because the tolerances are tight and costs are high. When you are at end of the process line, you are working with expensive chip from logic, you are dealing with a stack of memory, and once it's together, you cannot lose that final package. That's why the failure costs are really high when it comes to the advanced packaging. So what exactly is advanced packaging? So I will first go over a video. There is a video which explains in very layman's term what is advanced packaging. You have a memory chip, you have a logic chip, you place it on a substrate wafer, you go for the singulation, encapsulation, you reveal your TSVs, you create a bumps, and then you connect with silicon interposer, and then the other components also comes into a picture. Again, you go for the encapsulation, and that's how your final package gets ready. So there are multiple processes that comes together, the multiple use cases that comes together, and that's form one final package. So it's a very expensive as well as very tricky process to work on. So if you want to remember one phrase from this conference, then remember this, that advanced packaging is all about interconnect scaling. How do you scale your interconnect? How do you work with the higher bandwidth and how do you get the better performance? So it's all about interconnect scaling. So there are different technologies which currently R&D work is ongoing. Some are matured, some still need to explore ways of hybrid bonding, bridges, wafer and panel. Panel is a hot topic these days, where we can have a multi-chip integration. We can print a larger reticle on a panel. Glass core substrates, I think Raviji talked about, and then the co-packaged optics, what is coming next, how can we solve the energy loss problem, or how can we have a faster memory transfer. So if we talk about the hybrid bonding, now I will go and explain 4 key technologies. We'll start with hybrid bonding. So scaling of hybrid bonding is driving sensitivity and precision. Long back we had shoulder bump, from there we moved to copper pillar, micro bump, and then currently we are talking about the hybrid bonding where the pitch is shrinked less than 10 micron, and there is a roadmap of 1 micron as well. The height of bump decreased, the diameter of pad also decreased, so that's why the sensitivity of inspection, the overlay requirements, it's also became sub-micron or sometimes in nanometer. So it's very safe to say that packaging these days requires a process control more like a front end. What it used to be in the front end, now the ask is to adopt the same strategy on inspection and metrology on packaging as well. Glass core substrate, I think Raviji had better slide, and we have a same screenshot from Intel here. The offering from glass core, the advantages we have is you can have a fine line and space patterning and bump pitch scaling. You can have a tunable coefficient of thermal expansion, and there is a roadmap for future optical interconnects. But the challenges with glass core is that you need to handle that glass substrate, which is very fragile. You need to form through glass vias, the TGVs, which we call. So from process controls lens, glass core introduces a new maybe defect type and metrology requirements, especially around the geometry of the via. You need to ensure that you have penetrated well through the glass, and the structure of that via is solid. And it may also introduce the stress. So stress is also something which is a challenge on the glass. The other key technology which enables the advanced packaging is the panel. So as package size are getting larger, unit economics starts to favor the rectangle or a panel size. But if we compare it with the wafer, the 300 glass wafer, so wafers are compatible with the front-end equipments. You have a well-established ecosystem. You have equipments which can handle the wafer, which can load the wafer, check the wafer. The processes are matured. Wafers are there from many decades. The only downside is that you can only have few units at a large package size, maybe 5 units if we are talking about 91 by 91 interposer. So the advantage which comes with the panel is that you can have more units, and with 510 by 515 we will have 25 units in a same substrate. But the challenge is that you need to modify your front-end equipments, not just the inspection or metrology, but mainly on the process side as well. There are challenges with the coating and grinding, which I will talk about, and it's very difficult. We have seen that it's very difficult to yield the corner dice. It's not easy to get a high yield on a corner dice. So the challenges with panel, there are lithography challenges, then there are challenges with the deposition, how you will deposit your material. You need to ensure that the coating is accurate. When you grind for it, the grinding should be accurate. There are challenges with the panel warpage since the die size is larger or it's a new substrate, so we see a warpage on panel. Then we are revealing for vias. You need to ensure that your grinding is uniform. Otherwise, we may reveal some of the vias on the same substrate and the other side of the package will be unrevealed. And since it's a large package size, when it comes to the advanced packaging, it's all about the how do you integrate or how do you place your die on top of each other. So you need to figure out the accuracy as well for the assembly. There are challenges, but it's innovation which is continuously ongoing, and I think this is the future of packaging as well as the industry. I think, how many of you know about or have heard about this co-packaged optics? Okay, we have few. So co-packaged optics is a heterogeneous integration of optics and compute, which improves the bandwidth and energy efficiency. We started with pluggable transfer optics, then industry moved to onboard optics, and currently we are at co-packaged optics. So the goal here is that you place your optics closer to the compute, so you save on your energy, and you have a higher memory per bit, and you can transit your signal fast in an efficient manner. But in order to work with co-packaged optics, it's not just the advanced packaging. You need to work with front-end semiconductor, specialty semiconductor, and advanced packaging. Everything comes together, then only we can get the solution for the co-packaged optics. So now we have a basic understanding of what is advanced packaging, what are the key technologies that are enabling it. Now I will try to connect this technology with the process control solution which are required in order to manufacture them at a scale. It's not just about the innovation. We need to make sure that we are able to manufacture over and over with very high yield. So what it takes. So the story here is the evolution, adapting the front-end like solutions for the packaging and the back-end. That's what enabling the higher yield in packaging. But let's understand how much process control is needed. So if I'm starting a fab, how much percentage of my capital I should spend on the equipment? So it's mainly driven by three key ideas here. One is complexity, the second one is value, and the third one is product type. If I have a very complex device, which is not easy to manufacture, then I'm economically, I will be rationally spend more on the process control. Second thing is value. If I'm working on a chip which is very expensive, let's take a 3 nanometer, 4 nanometer TSMC wafer which costs around $20,000 to $25,000. So it's very expensive. So you spend more to protect your yield. And third is product type. If I have a reliability concern, the automotive industry where you cannot afford even one defect on your die, it can be very dangerous once if that die goes into your car. And if I have a large die. So basically this three key parameters, complexity, value, and product type is where you spend more. And AI or the advanced packaging, it checks every box. It is complex, it is high in value, and you are dealing with large die size and you are dealing with high performance as well. So KLS portfolio, it evolved in the last 4 or 5 decades. We have a differentiated product solution which works across the industry. There are solutions on inspection, review, metrology, on process side of it. Then there are solutions for chemical process control and the software solutions as well. But what has changed recently is how data flows across the tool. The modern industry or the modern process control is no longer a decision of one tool. You need to deal with multiple tools. You need to get data from multiple tools and need to analyze on a yield management system so that you can get something meaningful out of it and your process engineer can learn something from it. So to build that, KL has a differentiated portfolio on the advanced packaging. There are solutions on the process side, there are solutions on the inspection side, and then there are solutions on the metrology side as well. So advanced packaging, it started as a technology buy because it was a new technology a few years back, but now it's more about inflation buy, or it's ramping up, so you need more tools to get a better results out of your chip. So if I talk about the optical inspection solutions for the advanced packaging requires you to work across the domain. You need a solution which can inspect the unpatterned wafer. You need a solution which is high in throughput. So throughput is how many wafers we can inspect per hour. Then you need a solution for high sensitivity because your logic chip nowadays is less than 2 nanometers. So you need a solution which can detect defects in sub-micron or in a nanometer range, even in the packaging. So industry always used to balance the sensitivity versus cost of ownership. But the thing here is that you need right tool at right place at right process steps in order to capture the right defect. That's the bottom line. And when we have a portfolio, process engineers can choose which tool will work based on the technology that they are working on. And it's not just the inspection, review as well. So few years back, the advanced packaging, the defects were in micron. Now the defects we are looking for is in the sub-micron range or even sometimes in nanometer. So you need a solution, the same review for that as well. Same goes for the metrology. It's not just inspection. So if I talk about the metrology in packaging, also you need a solution which can measure the overlay. Since you are placing multiple chiplets on your base substrate, you need to make sure that those are well aligned. If it's a wafer-to-wafer bonding, you need to make sure that wafers are aligned well. There are solutions required on a film metrology side. You need to measure the CD, the shape of the wafer, along with solutions on the chemical metrology. So the application of this front-end like metrology in packaging is in still early days, but it's growing rapidly. And as interconnect pitch are shrinking, metrology is, I think, no longer good to have. It's must have these days in packaging as well. If we talk about specific example of hybrid bonding, then how hybrid bonding is raising bar across the industry. If we compare the micro bump versus hybrid bonding, then the sensitivity or the alignment accuracy which were in maybe in micron, now it's at a sub-micron. The interface defects which used to be 10 micron, 15 micron, now it's a sub-micron. So the customers, they care about how clean the interface is, especially with hybrid bonding where the pad dimensions are maybe 3 micron or 6 micron or 9 micron. You need to ensure that you are capturing defects which are sub-micron. Topography level, the recess which we see on the copper pads are in nanometer level now. The warpage also, it's tighter control on the hybrid bonding. But let me close with a key takeaway that I would like everyone to have from this talk or from this conference. So industry used to feel like one runner, the transistor scaling, which was carrying baton forward year after year, but it's not case anymore. It's a relay race today, where scaling of transistor matters, where the memory innovation matters, but advanced packaging is also one of a decisive runner in this race. And the relay races are won or lost based on where you hand off your baton. And that baton handoff is interconnect. How well your interconnect is, how good you can control your warpage, how well you can scale, how well you have a clean surface. So that's what matters today. And the advanced packaging, whether we talk about the hybrid bonding or glass core panel or maybe panels, it's not just the success is not defined only by the innovation. It's about how well you can manufacture. It's about manufacturable integration. So if you want to remember, then remember this: the future of interconnect, the future of performance is interconnect, and the future of interconnect is process control. With that, thank you. Thanks a lot.
Thank you, Hipang. So the key message is precision in every step of the process, profit in every package. Okay, thank you. So on that note, let me actually invite our next speaker, Dr. Suraj Rangarajan, an industry senior, managing director and principal technologist at Applied Materials, an old friend from my previous innings. Suraj is a technology geek, a brilliant manager, and I think a wonderful speaker to have this afternoon. So, Suraj.
Good afternoon. You've been listening patiently a lot. So first, thanks to Ashwini for the generous introduction. Thanks to the eminent panel. Thanks for inviting me to talk here. And thanks for holding this in a university setting. In the back, can you hear me? Back row, yes. Okay. So first thing, I wanted some more energy in the room. So let me start with a joke, right? Oh, wonderful. Thank you. Okay, I'll start with a joke. So all of you know honey, right? You buy honey. Most of the honey is adulterated. You know that? Show of hands. How many of you know that? The back row needs to wake up, okay? Okay. So this person finds out, right? Honey is adulterated. What do I do? I am going to make my own honey, right? I go to the pet store. So this person goes to the pet store and says, I want some honey bees, right? Give me 12 honey bees. And the person says, okay, here. And the person gives, the store owner gives 13 honeybees. And she says, no, I only need 12. I asked for 12. I need a dozen. I just want to get started slow. It's okay. You can keep it. The 13th is a freebie. Okay? People are still not awake. Front row got it? Yes. Okay. So first, I would like to thank all the people in the front, right? Just when that somebody called you 100 years old, right? So the semiconductor industry in India, right? I moved to India in 2007. A lot of people here. 2005, 2006 is when the first semiconductor policy was written, right? Many people here were involved in that. There was supposed to be a fab that came, right? 2005, 6, 7. 2011, 12, fab almost came, right? We all congratulated and announced and all that. 2016, display fab was supposed to come, right? Almost came, didn't come. Then now we finally, I think one of the things that the people in the back should be aware, right? Don't take this for granted. This is a journey that a lot of people here have put lot of time and effort and energy, and Ajit has traveled many, many times to India to make this happen, right? Big round of applause for Ajit to champion this. I've seen him in every ESA event championing that Fab Aayega for a long time. And Ravi has been driving the packaging story in every conference. And that's where we are starting with, right? The India semiconductor story is starting with packaging like all the other countries did. So the reason I'm taking some of this is now for the back, right? So semiconductor as a career choice is something that all of you should think about in the context of what is being talked about today, right? You will get a lot of information. You will not remember half of it. Remember 2 or 3 things. What Ajit Manocha said. Today, do you know how much the semiconductor industry was 2025? Any idea? How much was semiconductor sales in 2025? Anybody? Okay, 600-700. I think the latest numbers we had about a 20%, 700 billion, right? 790, 700s, right? A $700 billion industry, and now if you take the number that he's talking about, is going to triple, 3x in 10 years. There is no other industry. There is no other industry which will have this kind of growth of this size, right? So that's the first message I want all of you to take, that this is a growing industry globally. In India, this industry is starting, and we expect it to grow. Numbers go anywhere now from 100 to 500 as AI is going to scale and all that. So think about why you want to be in this industry, right? Then you hear a lot about all the different domains and all that stuff. I'll talk. So one of the good things about being back in the speaking order is everyone has made your points. One of the bad things is everyone has already made the points that you want to make, which is why I'm getting some time to do some of this evangelizing, right? I will go to slides, but first I want all of you to think, you are in this conference. Why are you in this conference? Because you are in an industry that is growing, and it's growing at a big rate. How many of you went to the AI summit? Okay, quite a few people. I was blown away. I don't know if I was blown away. I mean, just the scale of what was there, what I saw, and the possibilities, right? Amazing. I didn't expect, I didn't know what I expected, but what I saw, I was blown away by what I saw. That first, India is doing all this already, which is an amazing thing, right? Today, from an AI infrastructure, AI data center, associated stuff, right? CapEx spend is in the order of multiple hundreds, $800 billion, trillion every year being spent. Some of that will be spent here, right? Finally, at the end of the AI summit, they said about 250 billion. They have some commitments and all that. So that's another part, right? Other than all this, there is the AI infrastructure that's also going to be set up here. So think about which part of this semiconductor puzzle and the opportunity you want to be part of. There is VLSI, there is materials, there is equipment, there is packaging, there is all the AI-related applications. So this is to think about where you want to be in that. Okay, now I need to get my slides. Okay. Okay. How many of you know about Applied Materials as a company? The front row, the back row doesn't. I'll do a few slides just to set up what we are. And then I'll talk about some of the other slides. Most of the other slides people have presented in some form of the other. So I'll try to do contextualization of those slides. And then we'll come to what we want to take away. Again, 50-ish year old company. All the semiconductor companies were born around the same time. In India, we've been here for more than 20 years. So this is in Whitefield, Bangalore, 2002 when we started. This picture was taken in 2008. Applied Materials, innovation, collaboration, commercialization. Those are the things to remember as a company, what we do. So this picture is important, and the words there are also important. Material innovation. There was a very nice slide that was shown on materials. Ajit Manosha showed the different material parts. And I think that is one thing that I want all of you to think about. This whole industry is driven by materials, right? Material innovation is what has driven it over the past 50, 60 years. Every new thing that comes in semiconductor is a result of some material innovation. The way that we've taken the periodic table and been able to tweak performance out of materials. The other is scale. If you look at that person sitting in the left corner, that is a person as opposed to the size of the equipment. This is an equipment that's used to make LCD panels. The panel is probably the size of a garage door, about 2.5, 3 meters by 3 meters. That is the size of the glass that gets processed there. So that's the scale at which the industry works. this is a nice way of looking at what goes inside, right? Left-hand side is a 300 millimeter wafer. That's basically your large pizza, right? In your large pizza, you're looking at one die, which is like a postage stamp, 1 centimeter by 1 centimeter. In that 1 centimeter by 1 centimeter, if you flip it and you look at the transistor, that whole section, this is like a multi-story building. The transistor is at the bottom, and you have about 10 to 12 level layers of interconnect that takes the signal from the transistor to the top. So this is after you strip out all the dielectric and everything, this is the copper that's left. So what, it's about 60 miles of copper that comes in that small postage stamp. It's about 60 miles of copper, and this is going to get bigger and bigger. So think from an engineering achievement. Any engineers here, right? So this is the level of manufacturing, and this has to be done. It has to be done all over the world, and it has to work the same everywhere. That's the complexity of semiconductor manufacturing. And within that, over here, within the transistor itself, you have so many different materials all at the nanoscale. So the way to look at semiconductor manufacturing, you're doing things at atomic level, but at industrial scale. That's how to capture this industry. Many kinds of equipments, very simple, just like always I think of semiconductor like a multi-story building. You build, you add, you remove, you add, you repeat. So you deposit materials, you remove materials, you modify materials, you inspect materials, and that's how you keep building that. This is how a system, applied material system looks like, and the way to look at this is from a opportunity from an India perspective. What we are looking at is the bill of materials of this. Let's say this is a $5 million system. And if you look at all the parts, how many of these parts can be made here? That's one thing that, so forget all the high-tech stuff. Very basic, just the material in there. These are valves, electric systems, parts, components, lot of things that India does already today for aerospace. India does already for pharma. How can some of this be done here? So that's one thing that SEMI is driving, how supply chain can be developed in India. So another opportunity for people here in the room, semiconductor doesn't always need to be high-end VLSI, doesn't always need to be very sophisticated. Just building this tool is a big opportunity from an India perspective. R&D is a big part of applied materials. We have different R&D centers all over the world, and I'll come back to this towards the end. This APDC, Advanced Packaging Development Center, is one thing that I will talk about later. This is India, 5 locations, mostly in Bangalore. We have close to about 8,500 people, almost all in Bangalore, a few hundred in Chennai, about 40 in Coimbatore, about 10, 15 in Pune. We have a lab in Mumbai where we set up in IIT Bombay campus, where we have about 50 of our PhDs who work there on materials, and we also have a software group. This right-hand side was a sort of applied bug that we just created. This is about 3 months old. This is with the launch of our new campus. Okay, now we come to slides that others have already shown before. So this 1 trillion, all of us used this till last month. Everyone used this 1 trillion 2030, and this 1 trillion has now become 2026. About 975 billion is what the number is. And PPACT also, Ajit Manocha talked about that. Now the left-hand side of that probably is the important part from the India perspective. What is driving this and what is relevant to India? The data center opportunity is big. And that's one thing that the Indian government is pushing for. And that will happen. You've already seen announcements, Google and stuff. There will be data center being set up in India. The government is incentivizing that. Edge, IoT, robotics, there is a lot of desire from an India perspective to start using that. We will see how much smartphones we definitely use, then things beyond that. EV, AV, so the government had a 30% EV penetration by 2030. I don't know how strong that is anymore. We still need a lot of battery and we need charging infrastructure and all that. So there is that push. India is one of the places where there is still EV push. Another opportunity, power electronics, and this will grow, right? At least in the three-wheeler market and all that. Electric bus, we will see a lot more penetration here. And renewable energy. Actually, India has been growing a lot, and one of the things in October, we found that the grid is now the limiter. It is not the solar supply. There was about 12% rejection of solar into the grid. We are producing so much, our grid is not able to take it. So that is also a electronics, power electronics issue that we need to resolve. And these are connected. The data center requires power from renewable energy, which we should. So these are all very connected issues. So many people made this point about where issues are. One of the big things is the energy efficiency of the compute. The biggest thing that can stop AI today is the power requirement. If the power that an individual transistor consumes doesn't go down and the demand keeps going the way it is, we won't have enough energy in the world in 2035. So every time you ask ChatGPT, give me an answer for some simple question, oh, good morning. You say good morning to ChatGPT, that adds energy to this, right? So the energy consumption, one of the biggest things that will stop AI is energy efficiency. And advanced packaging is one of the ways to address that. So this point was made by all the speakers, everything going 3D. So from logic, gate all around, backside power, from DRAM memory, vertical 3D RAM, and also from a packaging perspective, the high bandwidth memory and the HI. Everything is going 3D. Others had much nicer charts on this. Ravi had a much nicer chart showing the workload increasing, and this is happening in the last few years, and the performance of the CPUs, GPUs are not able to keep up, and that's one of the big drivers of HI. And the other part is the size of the die. So the size of the die is getting bigger and bigger, and that's the two reasons why HI is going to become bigger as we move forward. Sorry, I went in the wrong direction. Okay, so these, again, everyone talked about these three trends that are happening from a advanced packaging perspective. One is, if you look at the right-hand side, if you look at a volume, in a cube, how many chips can you pack together, right? That's one. The left-hand side, how can you pack them closer together? And the third is, how can you pack more dies in a given space? So if you simplify everything that's happening in advanced packaging, these are the three things. How can you put more in a cube? How can you pack things closer together? And how can you put more in a given space? Just three problems that are all simultaneously being solved today. This chart was shown, and basically what we do today from an I/O perspective is to use bumps. These are solders, right? To make connection, you use bumps, and the bumps are not that efficient, and from a power efficiency perspective, and also from a space. So to bring things together and closer, we are now moving towards hybrid bonding, which is basically copper to copper. So, and the right-hand side of this, power efficiency, I think Ravi Mahan talked much better about that. This is how it happens. So essentially you take a die, maybe the next picture is better, yeah. So this shows the workflow of that. You create the damascene process, you do the plating, you do the CMP polishing, and then you do the surface prep, and then you put back to back so that there is a copper to copper compression bonding that gives better conduction, right? This is what, and I think AMD has demonstrated it. All the companies are now working on productizing and make this manufacturable. This is a tool that Applied has built along with a company called Bessie, a Netherlands-based company, and this does whatever I showed in that previous thing. All those steps together are done in this tool. The second part, Hemang talked about this. He had nice charts showing this panel. So very intuitively, if you take a die that becomes bigger and bigger and you try to put it in a round, so people who saw Apollo 11, that round thing in a square peg in a round hole thing, right? As your squares get bigger, your area utilization of a round wafer goes down. So, which is why the industry is trying to move towards a more square panel structure. And so they are still working on the standardization of that. 310, 505, 515 things are happening, but in the next year or two, this will happen. So you will start seeing panels show up. I think everyone made this point about glass being the the interposer. That so basically, silicon wafer for 300 was fine. Now, if you go to a much bigger panel, you need something which has more stiffness and can deliver the mechanical integrity and also the thermal expansion mismatch. And glass is a material that the industry is sort of converging to in this area. So this means that the entire workflow should change. The whole fab, which is today built on handling round wafer, needs to be able to handle rectangular substrates. So that's something, that ecosystem is also happening. So from an opportunity perspective, there is materials, there is machine building, there is just how do you design chips, lots of different areas. So one of the things that I would look at all of you to do is which one of this sort of appeals to the area of your interest, right? There are many, many, many opportunities. I will skip this and I will talk about, so when Ajit Manocha presented, he talked about industry needs to collaborate. And this is an example of Applied Materials collaborating in Singapore. So there is IME, which is institute in Singapore sort of dedicated to packaging. We worked with IME, we set up this clean room in IME premises. We worked with them, we co-developed a lot of processes, especially in the TSV time. And we have test vehicles available. So this is one thing that there is a collaboration opportunity with industries in India as they start going forward. There is already established standards, there are test vehicles, so we can use that as companies start setting up their lines. So that's one thing that I wanted to bring up. So I will skip a couple of this. Yeah, this is our head, Prabhu Raja. He heads the semiconductor group in Applied Materials. Recently, he was here in India, and his point, so the India industry semiconductor industry is starting with packaging, OSATs, ATMP. The value proposition is how do we move towards advanced packaging. The reason why everybody in this panel is talking about advanced packaging, that's where the value is. You learn how to do, you learn how to yield, you learn how to make chips, you learn how to do semiconductor manufacturing with conventional packaging, but the sooner we can move towards advanced packaging, that's where the value is for the industry in India. And my last slide, just to sort of summarize, there is how do you continue down the path of performance with advanced packaging? Equipment definitely is one way to build that, and then how do we leverage what we've already built? There is a center in Singapore that we can sort of deploy for this. So those were the three, but I definitely want to see from a audience perspective, right? What do you guys take from all this, what people have presented, and is there anything that you see which we can answer more on packaging, advanced packaging, and the opportunity that you see from a semiconductor perspective? I'll leave that open. Thank you.
Thank you, Suraj. Appreciate that talk. May I invite Rajesh Sharma ji, ICA to Executive Director and Principal Advisor at India Cellular and Electronics Association for a wrap-up note.
You need mic? No, I think this is okay. No need. Good afternoon. What a wonderful session we had from global leaders like Ajit ji, Ravi, Suraj, Hemang. As we conclude this inaugural session, allow me to place today's conversation in a larger national interest. India's rise as electronics manufacturing nation is no longer an aspiration. It's a reality in motion. We have already achieved in last 10 years, almost we have increased 6 times our electronics manufacturing output, as one of our previous speakers has said. 10 years ago, we were producing almost like 2 lakh crore, which is almost $25 billion of electronics. This year, we have produced almost $140 billion of electronics, and we are looking at producing $500 billion of electronics manufacturing output. In the semiconductor ecosystem, in last 2 years, we have committed more than $20 billion of investment, which will mature in next 2 years. One of the largest investment, as earlier speaker told, that Micron, which is almost $3 billion, that has been operationalized since yesterday. Commercial production is out. So the opportunities are huge. But we need to move from now volume to value, and that transition is precisely why this EPDMC is so timely and relevant. Packaging, design, manufacturing, and system integrations are where value is created, differentiated, and retained. Conferences like EPDMC are not just technical sessions, sometimes boring, but I think if you can get 10% out of it, it also that you have achieved for what you are present there. At ICA, we are increasingly seeing that the next competitive edge for India deep tech and electronic industry will be customer-centric. Demand understanding is the key, and what I will ask my young colleagues there, that all these companies which are presented by before me, Intel, Applied, KLA, they are all global companies. We call them global value chains. They have come here putting their solutions in front of us, establishing the capabilities here, but we need to create solutions. We need to create products which define the requirement of a 1.4 billion people here. So we should create our own products, we should create our own designs so that we can utilize the capabilities and the capacities which are being established in the country. The $20 billion investment which has already gone, another $20 billion will go in next when the ISM 2.0 will be announced in this sector, another $20 billion will come. So we will have a large manufacturing capacities established here, but we need our young generation to come forward and start building products. Products means the chips. You see how the complicated designs, how the complicated solutions are there to produce those chips. So we need that young people from the universities, along with, I will ask or I will request the professors of the institutes also to come forward to establish innovation center where they can utilize these facilities and create their own products. The opportunity before us are clear: align skills with real industry demand, integrate design, manufacturing and supply chains, build institutions and talents that think globally, but execute locally. Without global aspirations, this world is so integrated now, without the participation in the global value chains, if we have to make India as a reliable and resilient partner in this industry, we have to think global. EPDMC brings together exactly the convergence: academics, industry, innovators, and policymakers at the right moment in India's electronics journey. Let us use this platform to move decisively for manufacturing for scales to the manufacturing for the impact. Thank you, and I wish EPDMC all the best. Thank you.
Thank you very much, sir, for your encouraging words. Now, may I request Dr. Prashant Bala, sir, to please come forward and felicitate Mr. Ajit Manocha, sir. Please, sir, please come forward. A huge round of applause, ladies and gentlemen. Thank you very much. The next in the sequence is Suraj, sir. Suraj Rangarajan, please come forward, sir. Keep the applause going, guys. Thank you. Ravi Mahajan, sir, please come forward, sir. Thank you very much for coming here today and addressing the gathering. A huge round of applause. Hemang, sir, next in the sequence. Please come forward, sir. Rajesh, sir, please come forward. A huge round of applause. Sanjay Agrawal, sir, please come forward. A huge round of applause. In this conference, we have received more than 470 papers, out of which 77 got accepted, and they will be defended in the next 2 days, today and tomorrow. May I request the guests on the stage to please unveil the conference proceedings. May I request all of you to please come forward and unveil the book, Conference Proceedings for EPDMC 2026. "77 papers will be defended under 6 different tracks on day 1 and day 2, 2nd March and 3rd March. A huge round of applause, ladies and gentlemen. Thank you very much for joining us in this inaugural event. I request all of you to please proceed towards the tea break. It's on the ground floor, AG29 for delegates, and outside quadrangle area for the students, participants. Please. Thank you.